Okay, so again, maximum likelihood estimation says what values of my parameters can I choose such that I maximize the probability of observing what I observed. Does that make sense to everybody? Kind of a cool idea. Kind of a cool idea, right? In other words, what parameters are most likely to have arrived at what I actually saw in the world? Okay, so all of this hinges on us having a model that is a good representation of reality. Okay, if it's not, junk in, junk out. But if our model is a good representation of reality, then this question makes a lot of sense. I think my model represents reality pretty well. What values of my parameters would have been most likely to produce what I actually saw out in the world? Right. So let us ask the question, can we find maximum likelihood estimators for the, can we find maximum likelihood estimators for the mean and for the variance? Okay, separately. Okay. So we're going to do some partial derivatives. Here. Okay. So sorry, losing my voice. Okay. So this thing right here literally describes the probability that your first variable, right, your first sample value, I should say, is equal to some particular value, and the second is equal to some particular value, and the third. We are assuming that each one of these draws is independent and identically distributed. Independent is the key word there. Okay? If our stuff is independent, then the probability that this would happen and this would happen is just the product of their respective probabilities. Okay, I see some confusion on some faces. Let's think about this. Say that you're flipping a coin. Yeah, you're flipping a coin, right? What is the probability that you would get heads on the first coin? Sorry. Let's say coin. What is the probability you would get heads on the first coin? Excuse me. Coin 1 is equal to heads, and coin 2 is equal to heads. Okay. What is the probability you would get heads on the first coin and heads on the second coin?
Is that just 25% or?
How did you get there?
Because it's half. I guess, we're multiplying it together.
And why did you multiply?
I'm trying to remember why.
This is the same thing as the probability that you would get coin 1 of heads multiplied by the probability that you would get coin 2 is equal to heads. This is only true if the events are independent. In other words, if the outcome of your second coin was dependent magically on the outcome of your first coin, this relationship would no longer hold. Okay. We could do a deep dive into joint probabilities and conditional probabilities, which is where this comes from. Maybe I should have done that in the beginning of this class. But it will suffice, maximum likelihood estimation, it will suffice to believe me on this, that if our random variables are independent, this relationship holds. Okay. Coin flips, we can agree, are independent, right? There's no magical thread that connects the first coin flip to the second. Agreed? Well, this stuff, we have been told it's independent, right? We've been told that it's independent, right? We assume that the outcome of the first person I draw from a data set has no bearing on the outcome of the second person I draw from a data set. They are independent. So this, this must be equal to the probability that x1 is equal to x1, right? Multiplied by the probability that x2 is equal to x2, right? Multiplied by probability that xn is equal to xn. Ah. So, given that that's the case, our likelihood function, which is just the extension of this, very much related to probabilities, is that we have the, sorry, we'll just say L is equal to, this is a symbol people may not know, but I'll show it to you. This is what we call a product. So it's very much like sigma notation, except that instead of summing the stuff that's inside of it, we take the product of everything inside of it, right? So if each of these describes the probability, and that is determined by this function, what we have is the product of our function. We have 1 over square root of 2 pi sigma squared multiplied by e to the power of negative x minus mu 1 squared over 2 sigma squared. This is our likelihood function. Literally describes the probability that we would get what we got. How are people doing so far? Okay. So our goal is to try and maximize this thing. That's what we want to do. Okay? So we want to find the value. In this case, we're going to talk about with respect to mu, right? We want to find the value of this thing. I'm so sorry, my voice and nasal passages are working at it. We want to find the value of this thing that is maximized, right? That is as high as it could be. With respect to mu. That's what I want to do. I want to find the mu that'll make this as big as possible. Okay? All right. Let's start with that. I'll come over here. Use this stuff. So without getting, well, maybe. So I'm going to take the first partial derivative of the likelihood with respect to u, to mu, I mean. It's literally what I'm doing. I'm going to maximize this thing with respect to mu. When I do this, well, okay, sorry. Let me take one more step back because this is actually crucial, and I almost forgot to write it. This thing would be actually really hard to work with in terms of derivatives. It turns out that if we're trying to maximize this thing, this likelihood function, it suffices to maximize what's called the log of the likelihood. So if we take the natural log of this thing, it'll become a lot easier to work with. Okay? So I'm going to literally take the natural log of the likelihood function, and that'll be equal to, so the log of the products is equal to the sum of the logs. That may be a rule of logarithms people remember from that Augsburg trig whenever you learn it. Okay. The product, so the log of the product is equal to the sum of the logs. Okay. So instead of a product out here, I'm going to have a sum. I'm going to have a sum of I is equal to 1 to n. Okay. I'm going to have a sum of 1 over square root 2 pi sigma squared. Okay. And I'll write it for now, but then I'll explain what's going on, right? Sorry. This is equal to the log of, I'm trying to write intermediary steps and movements. I'm not doing a good job. Sorry. Don't write anything. So just okay. So I'm going to take the logarithm of this entire thing. Okay. When I take the logarithm of e to the power of something, the logarithm is going to bring down those powers. It's going to bring those powers down. Okay. Now, before we get there, let's just write this. Okay. The logarithm of the product is equal to the sum. I is equal to 1 to n is equal to the sum of the logarithm. So let's just start with that. Let's just start with that. People with me so far? Okay. And instead of a product, I now have a sum. Okay. Right? People can also see that this is the log of the product, right? So that must be the sum of the logs. Does that make sense to everybody? Right? So within this, right, now I've got the sum of I is equal to 1 to n, right, of this log, 1, 2 pi sigma squared, right? This is still inside of that sum, plus, right, plus e to the power of negative x minus mu, 1d squared over 2 sigma squared, right? Sorry, I missed a log. So sorry. Plus the log, that stuff. Plus the log, that stuff. Right? That should be true. Sorry to take so long to do that. Just to make sure that we know where we've been. We had this product, which is called our likelihood function. We took the log of that thing. This is the log of the likelihood. That's equal to the sum of the logs. The product, sorry, the log of the product is equal to the sum of the logs. So those rules of logarithms. So now I have the sum of the logs. Okay. Well, inside of here, I notice that I still have the logarithm of the product. Right? Well, that must be the sum of the logarithms. So now I have the sum of the logarithm of this plus the logarithm of this, all inside of that sum. Okay. Now I'm just going to break the sum up, because the sum is the sum of this stuff plus the sum of this stuff. You're welcome. It's the same as the sum of this stuff plus the sum of this stuff. Okay. So just coming over here. So I've got I is equal to 1 to n of log 1 over square root 2 pi sigma squared, right? Plus the sum of the log I is equal to 1 to n of e to the power of negative x minus mu 1 squared over 2 sigma squared. Okay. All right. So over here, we have the sum of a constant, the sum of the log of a constant, to be clear. Okay, that's still a constant. When we try and sum any constant, what happens?
Get constant back.
We get a constant back multiplied by however many times we tried to sum it.
Yeah.
Right? People remember if you take 2 plus 2 plus 2, right? That is the same thing as 3 times 2. Right? We tried to add 2 to itself 3 times, right? Same thing as 3 times 2. So this over here on the right side is the same thing as n multiplied by the logarithm of 1 over the square root 2 pi sigma squared. So far, so good. All right. We also need to know what happens when we take the natural log of something that's base e. Okay. These things are inverses of one another. They're inverses of one another. It's just going to bring down the exponent, and the logarithm of that e is going to become 1. Okay. So what's going to happen is we're going to end up with, this is, I'm going to write minus because this is a negative exponent. People can see that up there. So this is minus, well, before I even do that, let me, well, yeah, this will be okay. This will be okay. So let's say plus the sum of I is equal to 1 to n, okay, of, and I got to bring down the exponent. So I've got minus x minus mu squared over 2 sigma squared. People with me? Okay, I just bring down the exponent, and that has to get multiplied by the natural log of base e.
Just 1.
Which will be 1. Okay. Yeah, that won't matter. Just writing it down for your own notes for completeness. My own notes are much, much shorter than this. I like to write out intermediary steps, but work these out for a minute. So this stuff down here is a constant. It's not going to matter with respect to the sum. That's going to go to 1. So what we end up with is n multiplied by the logarithm of 1 over the square root of 2 pi sigma squared. Okay. I'm just going to bring out constants. Sorry, I don't know why that ended up inside there. It should have been on the outside. So sorry for any confusion. That negative symbol. So I've got a -1 out here, and I've got this 2 sigma squared, right? So I'm going to say minus 1, 2 sigma squared, right? Multiplied by the sum, I is equal to 1. And sorry, I've been missing subscripts. You guys will all forgive me someday. This is supposed to match what we have up here, which is for a particular xi. Right, so we're summing across the xi's, xi minus mu. Okay, this is our log likelihood. Okay. So what we want to do is maximize this thing with respect to mu. Okay, so I want to take the partial derivative of the log of the likelihood function with respect to mu. When I do that, I'm going to have the derivative of this, we'll look at the bottom one, this whole thing with respect to mu. Okay. Well, the derivative of this whole first term, right, for the subtraction, the derivative of this whole first term is going to be 0. It has no mu in it. It doesn't change with respect to mu. Okay, it doesn't change with respect. So this derivative will be 0 minus whatever's going on here, whatever's going on over here. So we get the derivative of, I'm just gonna, this doesn't depend on anything, it's a constant, okay? But we know that there's some mu terms that are gonna get saved in here. So I'm just gonna write the constant because it's gonna survive. So 1 over 2 sigma squared. 1 over 2 sigma squared. Multiplied by. Now, the derivative of a sum is the sum of the derivatives. Okay, it's a linear operator. Okay, so I'm just going to put the derivative inside of the sum and look at it. Okay. So I've got the sum of, sum of, sum of, and now I look at the stuff inside. Okay, so now I've got this xi minus mu squared. That is a function. Okay, we talked about this idea of the chain rule. It's one of our basic derivatives, one of our basic derivative methods. So the chain rule says, hey, take the derivative of the outside thing first. So the derivative of the outside thing is going to be 2 multiplied by whatever the inside thing is. That may not make a lot of sense. I can try and explain it a little better if you want. But what it boils down to is this whole thing is a function. Xi minus mu squared is a function unto itself, the function being square what's inside. The chain rule says take the derivative of the outside thing, which just brings down the 2 and maintains whatever's inside, and you multiply that by the derivative of what is inside. That's what the chain rule tells us to do. So you get 2 multiplied by xi minus mu, and then you multiply that by the derivative of the inside. The derivative of the inside. So this doesn't change with respect to mu, that's 0. This changes with respect to mu, right? It's got a power of 1. That's how often it changes with mu, right? So this ends up being 0 minus 1, right? Because there's 1 mu. It changes at a rate of 1 with mu, okay? 0 minus 1, okay? Which simplifies to, this whole thing simplifies to negative 1 over 2 sigma squared multiplied by the sum my I is equal to 1 to n to xi minus mu, right? Yeah, we'll simplify this a little bit more. Multiplied by negative 1. Okay, people with me? Well, I've got a negative 1 out here, a negative 1 back here. Okay, negative multiplied by a negative is a positive. Okay, so make this a positive. Okay, I've got a 2 here, right? I can bring a constant out of the sum without any harm to the sum. I've got a 2 here, right? I'm going to eliminate those. Okay, and I end up with 1 over sigma squared sum of xi minus mu. I is equal to 1 to n. Good so far? Okay. When we are trying to maximize, what we do is we set this thing equal to 0. Okay, as we talked about. Okay, when we have a single global maximum. Okay. So we're going to set this thing equal to 0. So 0 is equal to this thing. Okay. And now I want to solve for mu. Okay. Well, to solve for mu, I'm just going to work with what I have here. Sorry, bear with me 1 second. Let's see, do we need? Might need something. Hold on. Oh. Sorry, guys. 1 second. My notes are as clear as I thought they were. I know it's right. I was doing this earlier today. I might be wrong. Well, let's try and work it out. Let's see if my notes are just weird. Hopefully that's all that's going on. Okay. So, Okay, so this whole thing can be rewritten as 1 over sigma squared, right? I've got a sum of two different things. So this is 1 over sigma squared multiplied by the sum of xi, right? Minus the sum of mu. People are okay with that? Okay, so far so good? Okay. Okay. So I'm just going to distribute this thing in so that I have it everywhere, right? So I've got that this is equal to the sum of xi over sigma squared minus the sum of mu over sigma squared. Okay, people with me? Okay. The sum of mu, right, is just a sum of a constant. Can people still see if I write down here? Sam? Really? Yeah, Josh? Okay. So this is equal to the sum of xi over sigma squared minus the sum of mu is a constant, so minus n times mu over sigma squared. Okay. Now I'm just going to rearrange terms, okay, so that I bring this negative one over to the other side. I get n multiplied by mu over sigma squared. Okay. N multiplied by mu over sigma squared. And I get that is equal to the sum of xi over sigma squared. People with me? Okay. I've got sigma squared on both sides of the equation. I can eliminate that, right? Multiply both sides by sigma squared. Okay. So I get n multiplied by mu is equal to the sum of xi. I want to get mu by itself. Okay. I get mu is equal to the sum of xi over n. Does that equation look familiar? It might. If it doesn't, it's okay. Right? What if I wrote it like this? Which wouldn't be any different. 1 over n multiplied by the sum of xi. Does that look familiar? It might. Think about it for a second, because I don't want to rob you of the aha moment. You've seen this equation before. Seen it a lot of times, actually. You might use it in your regular lives. What is it? Okay, let's break it down. It's the sum. It's the sum of all of your observations divided by your number of observations. See what I mean? It's just the sample mean. That's all it is. It's just the sample mean. This is where it comes from. Turns out the sample mean is a maximum likelihood estimator. Turns out the sample mean is a maximum likelihood estimator. There are other ways to derive the sample mean. This isn't the only way, but it's kind of cool. This is a way to get it, right? All we wanted to do was find a good estimate of mu. That's what we wanted. Well, the sample mean is a good estimate of mu according to maximum likelihood. Kind of cool. Yeah. People with me? Okay. So this is what maximum likelihood estimation does. This is what it does. Okay. Now again, in this particular case, we have what's called a closed form solution. Closed form solution, right? We get a formula in there. Most of the maximum likelihood stuff we are going to talk about isn't going to work that way. It's going to have what we call a numerical estimation. Let's see. So we could do this. I'll skip over it unless people are really interested. But we could do this for the sample variance too, right? We just maximize this with respect to mu. We could also maximize it with respect to sigma squared. Okay? And we would get a formula that also looks very, very familiar. You would get this formula. You would get that our estimator of sigma squared is equal to 1 over n multiplied by the sum of xi minus x bar squared. That's what you would get if you maximized for sigma squared. Now, when you all learned the sample variance formula, you probably all learned 1 over n minus 1 instead of 1 over n. Well, this is the maximum likelihood estimator. 1 over n minus 1 is not exactly the maximum likelihood estimator. What that is a corrected estimator, because it turns out that this is biased. Maximum likelihood estimators often give us unbiased estimators, but they aren't guaranteed to. They aren't guaranteed to. What they will be is maximum likelihood estimates. They have to be by definition. They are not necessarily unbiased. Unbiased means that the expected value of this thing will hopefully give you back whatever the thing you were trying to estimate was. Well, that'll only work if you take 1 over n minus 1. Okay. That's how that works. Okay. Questions about the logic of maximum likelihood estimation? No? Okay. Then let's talk about All right, so let's talk about our next idea. Let me think about okay, I know the best way to do this. So, I don't know that this part will record, and I tried to post the recordings from last time, and then the Canvas app timed out on me, so I just need to upload those to YouTube and then share them with you. So in case you're wondering what happened to that promise, that's what happened to that promise. Okay. Apparently they are too large to upload. Okay. So then I'll turn off the overhead. Yeah. So I've tortured you all a little bit with a lot of math, right? With a lot of math. Hopefully it's interesting, right? I'm not asking you to do these derivatives, right? But I hope you can appreciate how they work. Okay. What I'm going to show you now is that the normal, sorry, let me back that up. The multiple regression problem we've been talking about, you can think about it from a maximum likelihood perspective if you wanted to. Okay. If you wanted to. So suppose that your very first person in your data set, right? We usually call that Y for your outcome. We usually call the outcomes Y. Suppose that we get some particular value of Y, right? And let's assume that Y is normally distributed. Let's assume that people's outcomes are normally distributed. Well, if we do that, we could build a likelihood function that looks a lot like the one we just had on the board. It looks a lot like the one that we just had on the board. So the probability that person 1 would get whatever they got, and person 2 would get whatever they got, and person 3 would get whatever, person n would get whatever they got. Okay, we could build that likelihood. But here, the parameters are not just the variance and the mean. The parameters have to do with our betas. They have to do with our betas, right? This is the likelihood, right? This is the likelihood. So it's the probability of all of this stuff, right? That for a particular actual observed yi, the difference from that and the predicted yi. right? Are people with me? Okay. There's a proof that goes into this, but basically what we're doing when we're doing multiple regression is estimating the expected value of people's y's. That's what we're doing. So in the probability density function, where we would usually see the mean, mu, what we actually have is our best guess for that person. That's our best guess at their mean, okay, which is why this ends up here in the numerator. I'm jumping a little bit forward, but how do people feel with all that? Okay, I see a nod at least, tentative. Okay, I might be moving too quickly, and if so, we can walk it back a little. But the idea is that this is the likelihood function, and we will seek to maximize this likelihood function with respect to beta. This comes from a paper I wrote but never published, so I'm allowed to distribute it as I want. If you want a copy of them, okay. Okay, so the question is, what values of beta, of our beta vector? Just to be clear here, beta is a vector. Everybody remembers there's more than one beta term here? Okay. What value of the beta vector would give us the maximum possible value of this likelihood? That's our question, right? That is our question. Okay. Now, very similar to what we just did, we're going to find the log likelihood of this thing, okay? So when you do that, you end up with this, okay, with this ugly mess right here, okay, where theta here represents the sigma squared, okay? It's just confusing sometimes to have a parameter that has on its own head its own square when you're actually talking about the parameter in its entirety, not just its unsquared version. Okay? That's the only reason I'm using theta here. Okay? But this is the log likelihood. This is the log likelihood. Ah, why do we care, people? Well, anybody ever learn ANOVA when you were taking statistics? What is ANOVA?
Isn't it a single variable? I think there's multiple variables, but I know the general one's a single, like it's a one-way ANOVA test. You use like a single variable and can get the different like predictors of if your variable is like a viable causation for what's going on.
Yeah, exactly. Something like that. So, just to remind everybody, in an ANOVA, what you were learning how to do was to test for multiple variables changing at once. And by changing, I mean coming into the model, right? So in the classic ANOVA setup, you might have something like a single variable with 3 or more conditions, right? People in group 1, group 2, group 3, right? That could be your treatment group, your half treatment group, and your no treatment group. You want to know, was there an effect among these people, right? It could also be a two-way ANOVA, where we have multiple independent variables, right? Each with at least 2 levels, right? So is there some kind of effect going on between boys and girls and also between treatment and control, right? It's a two-way. Okay. The ANOVA itself is what we call this omnibus test. It just says, is there an effect somewhere in all of these variables? Not necessarily does it tell you, yeah, it's the boys and girls differ. It just tells you that among all of the stuff you threw at it, there is an effect. Okay. Now, you could do post hoc testing. Maybe you did this. I don't know how far your stats classes went. You could do additional testing to say, I found an effect. Now I'm going to go in and try and figure out which effect it was. Okay. So ANOVA is this somewhat general method of model testing. Okay. It turns out that if you want to compare what we would call nested linear regression models. Okay, what do I mean by that? Let me see if I'm even still showing up in the recording, sort of. So I'll try. People have all this that want it. Okay. If you guys are like sort of tentatively with me, stick with me, because this is where stuff is going to get very applied very quickly. Okay. I'm gonna stay away from math land, at least the hard math land, for the rest of today. Okay, you guys have had enough of that. So ANOVA. ANOVA is actually a method that's a little more general than how it was taught to you. Okay? If I want to know this, okay, let's say that I have we'll call this my null model. Okay? Let's say that I have some null model, and it is that yi hat is equal to beta naught. It's my null model. It's my intercept only model. The only thing I am using to predict yi is the intercept. Simplest possible linear regression model there is. I don't have a single independent predictor. People with me? Okay. I'm basically, my X matrix in this case would just be the ones. Everybody remember that my first column of my X matrix is ones? That's all that makes it into the X matrix for this one. It's just a bunch of ones. Okay. Basically, what you could prove is that beta naught will basically be the mean of y. That's what it'll work out to. Okay, anyway. Okay, let's say that I want to compare this to some, we'll call this some alternative model. Some alternative model, okay? Where yi hat is equal to beta naught plus beta 1 multiplied by x1. If I want to know, let's make sure that we're all very clear on what I mean by this. If I want to know, is this model significantly better, statistically significantly better than this model? ANOVA could answer that. ANOVA could answer that. Now, what's going on if you're thinking back to your stats days, like I didn't learn it quite this way? What's going on is in your stats days, what you're doing is you're taking your model that has all of your independent variables in it, boys, girls, those could be variables in this model, control treatment, those could be variables in your model, and you are comparing that to the model that has none of them in it, right? So in that case, it might be something like your alternative model might be beta naught plus beta 1 plus beta 2, x2, right? Where x1 is just a dummy variable that codes for boy or girl, and x2 is a dummy variable that codes for control or treatment. People with me? You can ask the question, is this model significantly better than this model? Cool, huh? In addition, if you wanted to, I'll call this alt model 2, subscript it. In addition, you could also do this. You could write some alt model 1, which is equal to yi is equal to beta naught plus beta 1 x1. That is a model that I could compare against the null, or I could compare these two models. This comparison would tell me, sorry, just to be clear, if I compared model 2 to the null model, it would tell me if among all of the predictors I added, in this case 2, if that significantly improved the model. That's what it would be doing. If I compare alt model 1 to the null model, it'll tell me if adding this single predictor significantly improved the model, comparing to not having anything in there. Now, if I compare alt model 1 to alt model 2, it'll tell me if adding this second predictor significantly improved the model over having just one. Are people with me?
Yeah.
Okay. It's kind of a cool power to have. And it turns out you can do all of that with what we call ANOVA. Okay. Furthermore, it turns out that ANOVA is just a very special case of what we call a log likelihood ratio test. A log likelihood ratio test. In other words, if you can get the log likelihood of this model and the log likelihood of this model, you can compare them, statistically speaking. And you can see if there is a significant improvement by adding this additional variable. Okay, and that's what we're about to do in R. People with me? Mm-hmm. So, this ugly thing describes the log likelihood of a multivariate, multiple regression model. It's literally what it does. Okay, let's see how we would code that log likelihood in R. I've done this for you so you guys can follow along. You're welcome. Okay, right? So I've got it here. Can people read that okay? Okay, I just started with what we had last time, so I hope that this just works for you. Okay, you'll need to code these two new things. You'll need to program these two new things. They're pretty simple. Okay, one is literally the variance of the errors, quite literally just the variance of your E vector. And the other one is just your sample size, which is, there's lots of ways to get that. You can get the length of Y, you can get the number of rows in X, and however big your sample size is. If people say, copy that now. And I'll try, in case people get curious. Sorry, this will cover it up for just a second. I promise I'll move it. I just want to bring over the written form so that if anybody is curious, you can appreciate the mapping. Okay. Okay. And if it's not clear, this minus yi minus beta naught minus b1 xi, right, squared, that is by definition the residual sum of squares. Right? We know that, which is why in our typed version, we just go ahead and use RSS, right? Okay, I'll let people catch up. I'll go blow my nose in. I don't remember being sick when I woke up this morning, so if I am now clean. No.
Equation.
Okay. Did you try and run it? See if it runs?
So I need to go back and put it all the same. Right, we're just using the same ones that we had last time.
Okay, gotcha. I'll just sort of talk to fill space, but also to hopefully improve and make sure that we're all on the same page. This is literally the likelihood function. It's quite literally what it is, right? So in other words, let's be clear, with the parameter values that I have chosen using ordinary least squares, because that's how you got to your parameters, right? What is the probability that I would have gotten the data that I got, right? That is what we were calculating. Again, it's conditional on us believing our model is a good model, because this is all calculated from our model. Okay. Now it turns out, although we didn't do the proof, that the estimates from an ordinary least squares and from a maximum likelihood-based method of your linear regression will be the same. In other words, if we had actually taken this thing and maximized it, we should have gotten the same values of our betas that we actually got from our ordinary least squares. So plugging in those ordinary least squares, betas, and so forth into this equation will give us the same likelihood function, the same likelihood value, I should say, that we would have gotten if we would have maximized it the other way. Cool? All right, did everybody get this to compute?
Yeah,
And what value did you get?
I got negative 2,138.
Sorry. Let's make sure that I rerun everything because I've been messing with my computer lately. Okay, so I get negative 2138. Is that what everybody got? Beautiful. So congratulations, you all just computed the log likelihood value for the situation that we had in class. Okay, kind of cool, right? Now, what we had in class was this. Agreed? Agreed? I'll call this model 3. Sorry, these won't be in order. Okay. If you wanted to compare model 3 against model 1, we could do that. Let's do it. So I want to make a null model. So how do I do that? Okay. Well, here's how you do that. Okay. So you need a matrix. You need a matrix of the x's. You need a matrix of the x's that is just ones. That's what this first couple of rows is. I just need a matrix of x's that only has the ones in there. Okay, it's the most boring model you could ever have. Okay. And then we're just going to go through the same steps we went through last time. I need betas for just this null model, right? This just follows the exact same formula that we already had, except instead of my original X matrix, I've now got this X naught matrix, or X0, right? Then I need my error terms for this null model, right? My error terms for this null model, which are just equal to Y minus, right, my predicted values. I think the rest flows from there. Please ask questions. Oh, heaviest stool I've ever lifted. Oh. I do still hear some clicking. How are we doing, my friends? Okay.
You said the last 2 minutes.
Okay. I wouldn't worry about anything past this line just yet. Good. Okay. For those of you who are here, let's compare values. See if we agree. Okay. So log like not. Okay. I get negative 2,496 points some change. Good. Awesome. So that is the log likelihood value associated with your null model. Okay. With your intercept only model. Okay. The question is, well, sorry, Spencer, Sam, still working? Yeah, I don't want to rush you.
Yeah.
Okay. Yeah, half the programming is debugging, as we know. Let me know if you need a hand.
I was able to run it, but I got NA as my return, so it doesn't think it's a.
Yeah, it's unhappy about something. You want me to take a look?
I know, right there, yeah, I can. I'm just double checking. So.
Will you double check your exo matrix? It's trying to give you some warning here.
Yeah.
So here you
Oh,
say
this
n
one.
row 1, 0. I think you mean to n row x. So
Oh. Yes. You're right. It is like so that was not thank you.
so try that. And try rerunning.
Thank you so much.
So try rerunning.
Yep.
Nice.
Thank you.
Spencer, how's it going? Good? Okay, we now have 2 log likelihoods. I'm almost out of time. So this is probably, I'm amazed at how long things take, but I really shouldn't be surprised. So no homework this weekend. That's the news because we're not far enough. So just to let you know, one of the homework assignments is going to be to work with another model, and I'm going to actually have you maximize the likelihood numerically. That's what we're building to. We're not there yet. Okay, but let's also look at this. So we now have 2 log likelihoods, right? I have log like 0 and I have log like 1, right? Is that what I saved it as? I don't know why that one looks a little weird. Log like 1. There we go. Okay, it was broken before. That's what everybody has for their first one, right? Okay. So what we have is something called a -2 log likelihood ratio test. That's what it's called. So I'm going to literally take, I'll move this up so that everybody can see it. I'm going to literally take -2. I'm going to multiply it by the difference of the log likelihood for the null model minus the log likelihood for the first model. Okay. Okay. This will make it a positive value. That's one thing to take note here. You make it a positive value. Okay. Okay. And I really have run out of time, so I'll just show you this. Okay. So, well, this is closer to 716. The degrees of freedom are 3. So these -2 log likelihood ratios, which is literally what we just computed here, these have what we call a chi-square distribution. Chi-square distribution. Okay. And in the chi-square distribution, it'll have degrees of freedom equal to the number of terms we added or removed. Okay. So we are comparing the null model to our alternative model 3, where we added 3 terms. We will have 3 degrees of freedom. We will have 3 degrees of freedom, which is what this says. So this is our syntax for getting the probability out of a chi-square distribution at a value of 716 with 3 degrees of freedom. Okay. So in other words, what is the probability this would have happened? I would have gotten this value for my -2 log likelihood test. Okay. It turns out that it is tiny, infinitesimal. Okay. Yeah, ridiculously tiny. 7 times 10 to the -155th. So close to 0 that for all intents and purposes it's 0. Okay. I'm just going to say this and let you all go. Okay. What we've just discovered is that there is a significant gain, a significant improvement in our model from going from the null model to going from the model that has these 3 terms. Okay. We will use this logic next time to look at our actual data, right? Our child height data, right? And we will see which of our variables, if any, significantly improve the model, significantly help us predict child's heights. Okay. Questions I'll take, but otherwise you're dismissed because I don't want to hold you late. You're welcome.